Okay, so today we're going to talk about torque, and we're going to focus more on mathematical calculations, because we kind of already talked about conceptualizing last video. We talked about the torque wrench and basically how it all works, how we produce torque from that, and how radius and mass, or radius and force affect torque. Well, yeah, mass in this case, because, well, in certain cases, because force equals mass times acceleration. But right now, I'm going to bring about one of the most common torque problems that you may see in your physics class, okay? It's can be a little confusing at times. I'm not going to lie. There's definitely some stuff that's confusing about this that's to anybody. But I'm going to make more sense of it, and it'll make sense to anybody who goes to do this lab. So basically right here is we have a seesaw, okay? That's basically a first-class lever in the engineering world. It's a first-class lever, and basically a first-class lever is a seesaw that on each side you have your fulcrum in the center, okay? Each side you have a load, usually going down, okay? So like this, okay? If we were to draw a free body diagram, we would see that mg is going this way, mg is going this way for each one. It's the same, right? And it would have Fn going up and Fn going up, and then obviously our fulcrum would be supporting all of it, so mg and then Fn. Now, if it were to tilt to one side, we have a little bit of an acceleration that would affect it. But this mg and Fn is going to be greater just because of the fact that it's going to be greater than, we'll call this m1 and m2. Okay, it's going to be greater than, we could write the greater sign, m1, mg, and then it's also greater than m2. Right, because it's going to be both. It's going to be a sum of m1 and a sum of m2. So let's just say that. So mg in this spot is going to be this equal to the sum of m1 plus m2. It's the sum of them, okay? It's a summation, okay? Or you could also say Fn here, right? Because it's the same thing. It's going to be an equilibrium in this case. So we see the system is in equilibrium, okay? It's in equilibrium right now. I use these numbers 50, 50. We're just going to make these simple numbers, 50 inches, okay, for each side. Okay, now this is unbalanced right now, right? Because I'm center. This is a balanced system. Okay, therefore it's not going to tilt. It's not going to lean in any sort of shape, direction, or form. It's on a fulcrum. It is balanced. Okay. And actually, this force normal on mg goes all throughout the whole entire lever. But I just like to write it towards the end because you normally calculate your distance, your mass, or your force times your whole distance, right? You're multiplying it to this whole distance, okay? I just like to draw it to the end because it makes more sense to me, especially when you add a mass on there. It makes a lot more sense when you're adding a mass, okay? So basically what we see here is that if we were to adjust the angle at which this force is being applied, obviously, that's why we use sine theta in this case. Okay, but because torque is equal to force times radius times sine theta. We don't really need sine theta in this case because we're not really going to be worrying about a theta. When we put a box on this, right, we're not worrying about theta in between the box and this point. We don't care about it because we know it's going to be moving with the force of gravity. So we can kind of get rid of sine theta right away. Okay, and it's just sine of 90, which is equal to 1 anyway. So we really don't care about that because sine of 90 is equal to 1. Okay. So now what we're going to do is, if I add a mass to this, obviously what you think is going to happen is going to happen. It's going to shift to one side, right? So if I draw out the same exact scale, right, and I have 50 on this side, 50 inches on this side, okay, and I add my box over here, okay, my big green box, and let's say this is like, I don't know, 0.2 kilograms. It's huge, but whatever. It's just easier to use different numbers. So let's say this is a 0.2 kilogram box, right? Which is really, 200 grams? Because we're going to move the decimal place over 3 times, okay? So it's a 200 gram box, or 0.2 kilograms in this case. And what's going to happen is we're going to see that we move this thing over, all right? Actually, that's not that big of a mass. 0.2 kilograms is normal. But what happens is when we put this box here, the lever is going to tend to tip this way, and then this is going to tend to go that way. Okay, so what we're seeing is a torque, okay? We have a negative torque, and we have a positive torque here, right? Because this is going up, this is going down, okay? And then towards the left as well. Okay, so what we see here is, we see that what's happening is this thing's going to start to rotate. Okay, and we're going to wind up with it being something like in this direction, in this orientation, with, again, there's our big green box. Okay, but what we do is we correct it. Okay, so we adjust its center of mass. Now, however, the center of the mass of the stick never changes because the center of mass of the stick itself is the same. However, because we added material, I guess you could kind of say that it did shift, because this is the same as if I were to drill a hole in the stick, it would obviously change its center of mass. Instead, I'm adding a weight to the stick, so it kind of does essentially shift the center of mass, but I don't want to confuse anybody by saying that the center of mass doesn't change, because it kind of does, but at the same time, it makes it harder when we go do our calculations. So let's just describe it this way. Let's say that the center of mass of the stick itself doesn't change, but the system, it does, because we added something and it's going to shift it. Obviously, it's going to shift its center of mass this direction because we added this mass over here. So if you were to put a pencil on your finger, right, or this marker, for instance, right now I found its center of mass somewhere over here where the E is in Sharpie. But once I slide this over, it starts to tip, right? And now if I were to add mass to this, right, if I were to add mass to one side, it would cause it to shift this way. So its center of mass shifted in this direction. Okay, so basically in this case, what we're seeing is our center of mass is going to be where is going to shift towards the left, right? So you could say this as center of mass. Okay, it's shifting towards the left. All right, so we have to move our fulcrum then towards the left, right? Because this is our fulcrum. We have to move it this direction, right, to correct this system. So once we do, we're going to wind up with something more like, let's just say, we're going to wind up with something, we're going to have our box on the end as we did before. And then we're going to have our fulcrum at a different point now. We're going to have it at, so let's just say that the mass of our stick, we don't know the mass of our stick yet, but let's just say that let's say we move this all the way over. So now I got 20 inches on this side, right? I got 30 inches, right? Because now what I did was, let's use different colors here, okay? So this makes this a little bit easier to understand. So if I use the black, for instance, I use the black. I see that I'm going to actually use blue for this box. The box is now blue. Makes our lives a little bit easier to understand these different colors. If I use the black now to show where the line is, right, because basically before I had 50, right, this is my 50 right here to the center of this box. Now, once I move this over, 50, we'll say 50 is about right here now, right, and then we still have another 50 inches, like right here, right? So now on this side, it's like we have 70 inches on this side, or 80 inches on this side, and we have 20 inches on this side, okay? And it makes sense because we have to balance this out now. Okay, so this is our original part of the stick. Now we shifted this all over to get 20 inches on that side and 30 on the other. Now what we're going to see here is it's still a 20 kilogram box, okay? Or a 200 kilogram box, 200 gram box, 2.2 kilograms. So our fulcrum is now here, our pivot point. The one other major thing we see is that we have this line right here that goes green, okay? We don't care about this line, okay? Because what this did was this balanced our system out, right? So really what I'm seeing here, when I go to do my calculation, a lot of people will say to themselves, oh, okay, well, if I want to calculate the mass of the stick, first of all, that was our original question. We want to find the mass of the stick, right? Of this full stick, a lot of people think to themselves, well, we're not accounting for this piece right here, this piece of the stick, because we had the 0.2 kilogram mass, and when I go to do my ratios, I could set up a ratio here, right? I could say that torque equals the radius times the force, right? So basically, if torque equals the radius times the force, I'm really saying that torque equals, right? I'm basically saying that torque equals the force, which is mass times acceleration, times the radius, or the distance, right? Because r is equal to the distance, right? So this would be our r, and then obviously this is our r. Now, what we see here, though, is what r's we're actually using. So for the radius here, I'm going to use this whole region, right? I'm going to use this whole region in here, the 30 inches that I shifted. Okay, I'm going to use the 30 inches that I shifted for this radius. For this radius, I'm going to use, obviously, what's left over here. And then what I'm going to say is I'm calculating, though, the mass, because when I set this ratio up, I'm going to say that mass times acceleration equals times the radius equals radius times mass times acceleration. Okay, that's my ratio for each side. So I'm going to write this out a little bit better. So we say I have radius times mass times acceleration equals, I like to put that where the fulcrum is, times mass times acceleration. Okay? But what we see on this side is, this is where everybody gets confused usually. The radius is just this little portion here that we shifted. The reason why is because this portion here is what we used originally to cancel our stick, to put it at equilibrium. This 50 inches, we kept it at equilibrium with that and our original fulcrum point. And then when we shifted it, it adjusted, it moved the center of mass of the system over a bit. However, the center of the mass of the stick is the same. Okay? So the stick itself, so we have the radius now as this portion, or distance as this portion, and then the radius here is basically everything, well, once we get to the center, it's basically everything bound to this side, and everything bound to this portion is 30 inches, okay? So we 20 and 30, but now the interesting part about this whole calculation is that when I go to use, when I set this equal to radius times mass times acceleration, obviously on this side, I'm going to say that the radius is 20, right, times my mass times acceleration, so it's really just 0.2 kilograms times, I already have it in kilograms, right? So 0.2 kilograms times 9.8, I get 1.96 as my force, right? So I got 20 times 1.96, okay, is equal to my new radius, which is going to be 30 inches, right? I'm just using inches in this case. You really should be using like centimeters, meters. But you know what? Let's convert. So we could convert, but I mean, just for this presentation, I'm just going to use, we could say that this is 20 meters if you want. 30 meters, actually, that's probably better. So basically in this case, if we were to make this, we could just make this meters, it's easier. We just want to make this as easy to understand as possible. So we're just trying to get the concept down about how this system actually works, okay? So you have 20 meters times 1.96, and that's a big stick, a big seesaw that we have going here. But so we have 20 times 1.96 equals 30 times, and that's just this radius. We're not taking 80. A lot of people take 80. The reason why we're not, again, is because we're not accounting for this whole portion, because we're putting it in ratio to one another. And it's very interesting how this all works. Because look, now when I'm going to use my mass, I'm actually finding the mass of this whole section, right? I'm finding the mass of this whole entire side. So this is going to be my mass. This is going to be my radius, okay? And then this is my mass over here, and then this is my radius. So what I do is, by doing mass times the radius, over here, I'm accounting for this radius, but now this is canceling that. So really what's happening here is, when I use this big mass to this small radius, I'm going to wind up getting the same torque as this side, right? And basically not accounting for this radius. I'm counting for only the mass, because they're going to cancel out, okay? And it's very interesting, because you don't really see that at first, but because I'm only using the small radius, if I use exaggerated equations here, which I used to love to use because they really make sense conceptually, but for this side, I'm using a big mass, and obviously I'm going to be solving for mass here, right? Because what happens is gravity actually cancels, right? Because I have mg equals mg. So in this case, acceleration, mass times acceleration of gravity cancels. But I want to wind up getting two different masses. I have mass 1 and mass 2. Okay. But we see here is that basically what happens is these cancel out. Because I have a huge mass over here. Here's my exaggerated equations. I have this huge mass, but a smaller radius. So a radius that's smaller equals, right? And on this side, I have a big mass, but I have a bigger mass, but a smaller radius. So this winds up canceling out, because in proportion, I'm setting this in proportion. I'm taking away, now that I got this huge mass, I'm using only the smaller radius to account for this radius here, right? Because instead of using this longer radius, because if I were to put this huge radius in, this huge distance into this whole entire piece, I'd actually wind up getting a smaller mass of the stick. And it makes sense because I'm dividing away more mass, but in proportion, I'm actually going to be using the radius that's changed over the distance. So the distance, I'm actually calculating the mass of this whole piece, but only the radius of the portion that shifted to put it in proportion and get the whole mass of this whole entire long piece. Because now this distance that I took away accounts for this distance over here, which is really interesting. So I'm actually going to be counting for that radius there. So this radius actually kind of cancels a little bit. But I wind up getting the radius of 50 on this side, where I get the radius of a much smaller piece on that side. But it winds up canceling because I have a little bit of a radius here. So this radius is going to wind up canceling now with a little bit of that radius. So I get the mass times the radius of just the stick itself. So that's how you get the mass of the stick. It's very interesting as you look at this conceptually, and you don't really see it at first, but it makes sense. I'm taking the mass of this whole piece, the radius of just a small portion that's shifted, and now I have the mass times the radius over here. But the thing is, I don't know the mass of this radius of the stick. I don't know the mass of the stick right here. I know the mass of this mass, but I don't know the mass of the stick. So to account for that, the mass of this stick is the mass that shifted. So I'm using this whole mass that shifted, right, and putting it in proportion by using the smaller, because this whole mass is really what I'm calculating plus the mass of the stick. But I'm using the smaller radius, which puts it in proportion to get the torque, right? Because I'm saying that mass times the radius equals mass times the radius. So on this side, it's 20. And then on this side, it is 80. So 80 minus 20 is going to be clearly 60. So I wind up doing 60, but now I'm actually, and that's my radius, sorry. But now I'm actually using that to a bigger mass on this side, a great mass times 20, times obviously the mass of the whole entire stick. So these wind up canceling. Okay, so you wind up getting 40, but it puts it in proportion. Okay, so it's very interesting how it works. It's basically using proportions to calculate the fact that you're calculating the mass of this whole stick, this whole entire stick, by using only the radius that's shifted, not this radius. You're basically ignoring this piece. However, you're ignoring it because it's shifted, okay, from equilibrium. So it's very interesting in this case. So thank you for watching. I hope I made a little more sense of this type of problem. It is a little confusing. It really is. You got to look at it and really understand what's going on in the system. Thank you for watching, and please leave comments if there's any more confusion. There's definitely different ways you can explain this. I think the easiest way is just to look at this physically and say that, we're looking at the radius here, and we have this huge mass. That's taking the mass of this piece of the stick right here into proportion into the final calculation, getting us the mass of our stick. Okay, so I really hope that was a good conceptual video. I hope it helped people understand. I hope it helped you guys understand that, the way that this actually works at this fulcrum point. Thank you for watching, and please leave comments.